ever have like a million tabs open, Spotify blasting, and you're like,
Yeah.
how does my computer even
Yeah.
handle this? Welcome to the deep dive. Today, we're tackling how operating systems wrangle that digital chaos
Right.
with this thing, this concept called a process. Get ready, you're about to see your computer in a whole new way.
It's true. This is fundamental stuff to understanding how computers actually work, not just like
Right.
some tech jargon.
Yeah, because it feels magical. Like my computer's juggling 100 things at once. How does it even...
It's all about processes.
Oh.
So every single thing you open, every app, every file, that's a separate process that the OS, your operating system, has to manage.
Okay.
It's like, imagine a chef in a super busy kitchen. Each dish needs attention at the right moment, the right ingredients, right?
Yeah.
Processes are like those dishes, all competing for the computer's resources,
Oh, okay.
like processing power and memory.
So is that why my computer slows down when I have too much going on?
Exactly.
Like the chefs run out of stove space or something?
Exactly. It's like trying to cook a 5-course meal on a single burner.
Uh-huh.
The OS can only handle so much at once. But to keep things organized,
Okay.
each process needs a way to be tracked. Like, think of a recipe card.
Yeah.
This is where the process control block, or PCB, comes in.
Okay.
It's like the chef's notes for that recipe.
So it's not just total chaos back there.
Right.
There's a whole system.
Exactly.
What kind of things are actually on this recipe card, this PCB thing?
So the PCB stores crucial information about each process. Imagine you're reading a book, right?
Yeah.
You put it down, you want to remember where you left off.
Yeah, for sure.
The PCB is like a bookmark for the
Okay.
process,
Gotcha.
remembering which line of code to run next.
Oh, okay.
And it keeps track of what resources the process is using, like ingredients.
Makes
I
sense.
had
So
to-
it's like each process has its own little
Exactly.
file folder almost.
Exactly. Yeah.
But how does the OS actually, like, switch between everything so fast?
Right.
1 second I'm on email, the next I'm watching a video.
That is what's called a context switch. Imagine the chef
All right.
checking the oven timer on one dish, then adjusting the flame on another.
Okay.
That's a context switch.
Gotcha.
The OS saves the current state of one process, loads another so quickly, you don't even realize it's happening.
That's incredible.
Right.
Now, our research also mentioned different process states, like new, terminated,
Right.
suspended.
Right.
I'm guessing terminated is the burnt dish?
Hopefully not.
Okay.
Think of terminated as the finished dish.
Okay.
Cleared from the table.
Okay.
A new process is like prepping ingredients.
Gotcha.
Not cooking yet, but it's in the pipeline. And suspended.
Yeah.
That's putting a dish on hold. Maybe the sauce is simmering. Chef needs to sear something else.
Okay.
It's paused, but it can be resumed whenever it's needed.
This analogy is so helpful. It's making a really complex topic
Right.
kind of click.
Yeah.
So just to recap, every app, every task, it's a separate process, right? With its own instructions, its own resources, like a recipe. And the OS is like the master chef,
Exactly.
keeping everything running smoothly
I like that.
in our computer.
Yes.
That's pretty cool.
It really is. And once you understand that,
Yeah,
it gives you a whole new appreciation of what's happening
it does.
every time you use your computer.
It really does.
Yeah.
Wow. So to our listeners, thanks for joining us for this deep dive into the world of operating systems. We just scratched the surface, but hopefully
Yeah.
you've got a new appreciation for this intricate dance of processes happening inside your devices right now.
Absolutely.
Let us know what you thought, what your aha moments were.
Yeah.
Until next time, happy computing.
Yeah. Happy computing.
Ever find yourself wondering what kind of sorcery keeps your computer humming along when you've got like a zillion things going on at once?
Yeah, it's kind of mind-boggling when you stop to think about it.
Well, get ready to demystify the magic, because today we're doing a deep dive into the world of processes and virtual CPUs.
Sounds a little technical.
It is a bit, but trust me, it's way more interesting than it sounds. We're basically going behind the scenes to understand how computers juggle everything we throw at them, from streaming movies to editing photos and everything in between. And our main source material for this deep dive is this article right here. You ready to jump in?
Absolutely, let's do it.
Okay, so the article jumps right into virtual CPUs. Have you ever heard that term before?
Oh, yeah, definitely. It's one of those things you hear thrown around a lot but might not have a solid grasp on.
Exactly. It's like virtual CPU sounds important. But what does it even mean? Well, the way I understand it is each process basically gets tricked into thinking it has its very own dedicated CPU. It's like a little white lie that makes everything run smoothly. What do you think about that?
Yeah, it's a really clever illusion that modern operating systems use. The truth is, most of us have one physical CPU or maybe a few cores if you have a more powerful computer, and those cores are constantly switching between all the different programs you have running. It's like a super fast juggler keeping all those bowling pins in the air.
Okay, so it's all about sharing.
Exactly. Time sharing is what they call it. Each process gets its own little slice of time with the CPU, and it happens so fast that it feels like everything is running at the same time. Pretty amazing, right?
It really is. It's like, how does my computer not just melt down when I have like 20 tabs open, music playing, and I'm trying to edit photos all at the same time? It's mind-boggling.
It really is a testament to how sophisticated our devices have become. And speaking of things being split up, one thing that caught my eye in the article was how applications themselves are often divided into multiple processes. So it's not just the operating system juggling, it's also the programs themselves are designed this way, right?
Oh, so it's like processes all the way down, huh?
Yeah.
It's like, wait, it's not just one thing. It's a bunch of smaller things working together. That's kind of blowing my mind right now.
Yeah, it's kind of like realizing the juggler isn't juggling bowling pins, but each pin is made up of smaller, interconnected parts that are all moving in sync.
So, like, what's the advantage of breaking an application down like that? Wouldn't that make it even more complicated?
You would think so, right? But actually, there's some really good reasons for it. For one, it makes the software more stable.
More stable? How so?
Let's say your web browser was just one giant process. Now imagine if one web page crashed.
Oh, no.
Yeah, the whole browser could freeze up, right? But by separating things like web page rendering, file downloads, and video playback into their own separate processes, even if one crashes, the others can keep running. Your whole browser is less likely to crash.
Oh, okay. So that's why sometimes only one tab crashes, not the whole browser. I've always wondered about that.
Precisely. It keeps things contained and prevents those annoying full-on crashes. The article also mentioned something about simpler interfaces being a benefit. Did you catch that?
I did see that, yeah. What's that all about?
Basically, it comes down to how software is developed. Imagine trying to write a single program that handles everything a web browser does, displaying texts and images, downloading files, playing videos. The code would be an absolute nightmare.
Yeah, I can imagine.
By dividing these functions into separate processes, each with a more specific purpose, developers can create cleaner, more manageable interfaces for how those processes interact. Kind of like having specialized teams within a company, instead of one giant, chaotic team trying to do everything.
Okay, yeah, that makes a lot more sense. Divide and conquer, right?
Exactly. And when developers have well-defined interfaces between processes, it's easier to update or fix one part of the application without breaking something else. It's a win-win for developers and users.
This is all starting to click now. So to recap, we've talked about what the mechanics of processes and virtual CPUs, right?
Right.
But now for the bigger question, the why. Why should we, as everyday computer users, actually care about any of this? It's not like you're writing code or anything. Does it really matter if we understand how processes work?
That's a great question, and it's something I think about a lot. It's easy to take technology for granted. We just expect our devices to work. But I think there's real value in understanding at least the basics of how things work under the hood. It's like knowing a little something about the engine in your car, even if you're not a mechanic. It helps you appreciate the complexity, make more informed decisions, and maybe even troubleshoot problems more effectively.
So instead of just hitting a button and hoping for the best, we can actually understand what's going on behind the scenes. I like that. It's like empowerment through knowledge.
Exactly. And this knowledge can be surprisingly useful in practical situations, too. For example, when you see a new laptop advertised as having a quad-core processor, you'll know that it potentially has 4 physical cores, which means it can run 4 processes simultaneously, which leads to smoother multitasking and better performance.
So the more cores, the more processes it can handle at once. That makes sense.
Exactly. And with the rise of multi-core processors becoming more and more common, this knowledge is only going to become more relevant as technology advances.
It's like peeking behind the curtain and realizing it's not magic, it's really ingenious engineering.
Absolutely. And as we rely more and more on multi-core processors in our phones, laptops, and even in our refrigerators and cars, it'll be fascinating to see how these concepts we talked about today might evolve in the future.
Maybe one day, we'll have so many cores that the lines between physical and virtual CPUs will blur even further. Who knows? Anyway, that's something to ponder. Thanks so much for joining us today. I hope you enjoyed this deep dive into the hidden world of processes and virtual CPUs. It's definitely given me a lot to think about.
Me too. It's always fun to dig into these fundamental concepts.
Absolutely. And hey, if you're listening out there, let us know if you had any aha moments along the way. We'd love to hear your thoughts. Until next time, ever find yourself wondering how your computer manages to run so many programs all at once?
It really is kind of like a magic trick, isn't it?
I mean, streaming videos and editing photos while I'm also trying to check my emails.
Yeah.
It all just seems to happen, you know?
Yeah, and the secret sauce behind this whole illusion is something called a process control block,
Okay.
or PCB for short.
So PCBs.
And in this deep dive, we're going to take a closer look at these essential building blocks of operating systems.
For those of us who aren't operating system, wizards,
Right.
what are we talking about when we say PCB?
Imagine this. Every time that you open up an app on your computer, it creates this really detailed behind-the-scenes file about it.
Okay.
And this file, so to speak, is the PCB, and it basically acts like the process's own personal ID card. And it holds all the crucial info that the operating system needs to manage it.
So it's like a digital fingerprint
You got it.
for every single program that you're running.
Exactly.
That's wild. So what kind of information is on this ID card?
All right, well, first up, you've got your CPU state. And this is basically like taking a snapshot
Okay.
of exactly what the process is doing at any given moment.
Hmm.
So if the process needs to be paused, say to let another program have a shot at the CPU, the operating system can just use this snapshot to seamlessly bring it back later on.
Oh, so it's kind of like hitting the pause button on a movie.
Exactly.
You don't lose your spot.
You got it.
So it's almost like the operating system is juggling all of these paused processes.
Precisely. And to keep track of whose turn it is next, you have the process state field. And this one tells the operating system whether a process is currently running, or if it's waiting patiently in line for the CPU, or maybe it's blocked because it needs something like data from the hard drive.
It's crazy how much is happening that we don't see. So what else is packed into these PCBs?
Oh, there's a lot more where that came from.
Okay.
You can think of a process's memory allocation, like its workspace,
Okay.
and then there's its scheduling information, which basically dictates its priority level in the queue for the CPU.
Uh-huh.
And then, of course, we need to keep track of how much CPU time each process is using, almost like a usage bill.
Right.
But instead of money, it's all about competing for that processing power.
It's like the operating system is a very meticulous accountant.
It is. It has to be.
It really does. So it sounds like each process has its own little world, just contained within its PCB.
Absolutely.
But these worlds can interact too, can't they?
They can. Processes can have family ties, believe it or not.
Okay.
The parent and children fields in the PCB actually show which processes are related to each other and how they depend on each other.
So if a child process starts acting up, can the parent process step in and be like, all right, get to your digital room?
In a sense, yes. A parent process might need to pause or even completely terminate a child process if it's causing problems.
Right.
Or maybe if it's hogging too many resources.
Yeah.
It's all about maintaining order and making sure our digital world runs smoothly.
That's super interesting. But I do have to ask, how does an operating system handle what could be potentially millions of these PCBs without getting totally overwhelmed? I mean, it would be like trying to organize a library with billions of books that are constantly changing.
Absolutely. Managing all of those PCBs efficiently is honestly one of the biggest challenges in operating system design.
Right.
There are two main approaches that are used, arrays and pointers.
Okay.
Each of those has its own pros and cons.
Okay. So arrays and pointers, those do sound familiar.
Right.
Could you give us a super quick refresher?
Of course. Think of an array like reserving an entire floor in a skyscraper for offices.
Yeah.
Even if you only need a handful.
Right.
It's simple, but it could be a huge waste of space.
Yeah.
Especially when you're talking about potentially millions of processes.
Right.
Pointers, on the other hand, are more like having a directory that points to offices scattered all over a city.
So instead of reserving a whole floor, you just use the space you need.
Exactly.
That's much more efficient.
You got it.
So which approach is more common?
You know, it really just depends on the operating system.
It's okay.
But this is where things get kind of interesting, especially with Linux.
Okay.
They've come up with this really ingenious method that actually avoids the overhead that comes with traditional linked lists.
Wow.
They use pointers in a really clever way.
Okay, now I'm intrigued.
Yeah.
What's so special about Linux's approach? What's so special about Linux's approach?
Well, imagine like a traditional linked list.
Okay.
It's kind of like a chain, right?
Okay.
Where each link is connected to the next one. So
Right.
to like add or remove a link,
Right.
you got to mess with those connections, which can get kind of slow,
Especially with a long chain.
especially with a long chain. Yeah, exactly.
Yeah.
So,
Like trying to reorder a real chain.
yeah, exactly. Like you're sitting there with a big old chain trying to rearrange the links.
Exactly.
So Linux actually gets rid of that whole chain structure altogether.
Why?
Yeah, instead of having one central list,
Yeah.
each P3V in Linux
Yeah.
has these fields for like younger sibling and older sibling.
Okay.
It's like a family tree
Huh. Interesting.
where every member keeps track of their siblings
Okay.
in the order they were born
That's it.
within the operating system.
Okay, so no more like cumbersome chain.
Nope,
Just a family tree.
you got it.
And everyone knows their place.
Precisely. And this is what makes it so much faster.
Okay, so how does that actually like speed things up?
Because now, to add or remove a process from this family,
All Linux has to do is just update a couple of the sibling pointers on a few related processes.
Okay.
There's no need to like go through this whole big long list.
Oh, that makes sense.
It's all about efficiency.
Yeah.
Especially when you're dealing with, thousands or even millions of these processes.
Distributing those links.
Yeah,
So you don't have the bottleneck of that one central list.
exactly.
That's really clever.
It's a really neat solution.
It really shows how these like little design choices
Yeah.
can have a huge impact.
Huge impact on performance for sure.
So we've talked about PCBs and how they each represent a process with its own little world
Right.
and how the operating system's cleverly organized in all of them.
Yes.
But how does this all actually work to run our programs?
Okay, so to understand that,
We have to introduce this concept of a ready list,
Right.
or RL for short.
All right, RL, got it.
And you can kind of think of this like a queue of eager shoppers all waiting for their turn at the checkout counter.
Okay.
So every process on this ready list
Yeah.
is like prepped and ready to use the CPU.
And so the checkout counter is the CPU.
You got it, the CPU exactly.
Got it.
But just like in real life, some processes get priority over others.
Of course.
Right.
So not all processes are treated equally.
Exactly.
Is that where the scheduling information we talked about earlier comes in?
That's exactly it.
Okay.
That field in the PCB helps the operating system figure out,
Right.
which process gets to go next.
So it's like a pecking order
It is a pecking order.
for processes.
Yeah, so like a really high priority task. Like something that needs to respond to your mouse click,
Right.
that's going to get bumped to the front of the line.
Of course, yeah.
Whereas something that's lower priority, like a background download, might have to wait a little bit longer.
So it's like this constantly shifting queue
It is.
with processes getting bumped up and down
Yep,
based on their priority.
absolutely.
It really makes you think about how much is happening behind the scenes.
It really,
Even when it seems like our computer's just sitting there.
you're right. It's wild.
It is. So we've talked about how crucial these PCBs are
Right.
and all the crazy ways that operating systems manage them.
Yeah.
But what happens when things go wrong?
Oh boy.
In this super organized world of processes and pointers.
Well, imagine for a second like a chef at a really busy restaurant and they suddenly lose track of all the orders.
Oh.
Dishes would come out at the wrong times, ingredients would be running out, and customers would definitely not be happy.
Sounds like a recipe for disaster.
It would be total chaos in that kitchen.
So that's kind of similar to what happens when PCB management goes off the rails.
That's a really good analogy.
Right.
Processes might not get tracked properly. Priorities could be all messed up, resources might not be released like they should.
Oh, no.
It could lead to a system crash, the dreaded blue screen of death,
Right.
or even just a really slow and unresponsive computer.
It's like the digital equivalent of indigestion.
Exactly.
So we need a well-maintained PCB system
We got it.
to keep our digital lives running smoothly.
100%.
They're like the unsung heroes
They really are.
of our computers.
Yeah, absolutely.
Yeah.
These little invisible structures are what make everything work.
Yeah.
They are behind multitasking resource sharing,
Right.
even the overall stability and security of our entire computing experience.
It's honestly mind-blowing
It is.
when you really think about all of that complexity
Yeah.
and how we just interact with it every single day without even realizing it.
And you know what? As we move towards even more complex systems
Yeah.
with like massive cloud platforms and AI and all that,
Right.
this whole PCB management thing becomes even more crucial.
Yeah.
Figuring out how operating systems are going to handle all of that.
Right.
That's a huge question for software engineers moving forward.
That's fascinating. So next time I open up a bunch of tabs and stream a movie and I'm chatting with a friend,
Yeah.
and my computer doesn't explode, I'm going to thank the PCB
You got it.
for making it all work.
Working hard behind the scenes.
That's right. Well, this has been a fascinating deep dive, I've got to say.
It has been fun.
Thank you so much for taking us on this journey
My pleasure.
into the heart of the computer.
Anytime.
And to all of our listeners out there,
Yeah.
if this deep dive has piqued your interest, go out there, keep learning, keep exploring.
There's so much out there.
There's a ton of really cool info out there about the magic that's happening
Absolutely.
inside your devices.
Yeah, it's amazing what's going on in there.
Thank you so much for joining us today.
Ever get that feeling like your computer is juggling a million things at once?
Oh, yeah.
Like a busy city with data zipping around, applications popping up left and right. Well, today, we're diving into that world, the fascinating world of how operating systems actually manage all that chaos.
Yeah, it's really is fascinating. You could say it's a bit like being the ultimate air traffic controller,
Ooh.
except instead of planes, you're dealing with processes,
Huh.
the lifeblood of any computer system.
Okay, so for anyone who's not fluent in computer use, let's start with the basics. What exactly is a process?
So in the simplest terms, a process is a program in action.
Okay.
When you open your web browser or start typing a document, you're giving life to a process. Each of these processes needs its own space, its own resources, and it needs to be able to play nicely with others.
Sounds like it could get chaotic pretty quickly. So how does the OS even begin to keep track of all that?
That's where the concept of process creation comes in. And believe it or not, it all starts with a function called create.
Of course.
It's kind of like issuing a passport to each new process. And this passport is the PCB, or the process control block.
Okay.
Without it, the process is stateless. It can't do anything.
Interesting. So the PCB is like the process's official documentation. What kind of information does it hold?
It contains everything the OS needs to know about this process. A unique ID number, its current memory location, what it's allowed to access, and even who its parent process is. Because just like in a city, processes often spawn new ones, creating a sort of family tree.
Ah, so it's all about maintaining order, making sure each process knows its place and has what it needs to function. But what happens when a process is finished doing its thing? We can't have them just hanging around forever, hogging resources.
No, definitely not.
Like that friend who never leaves your couch.
Exactly. That's where destroy, the counterpart to create, comes in. When a process finishes its task, encounters a fatal error, or is simply told to shut down by the parent, destroy swoops in to clean up the mess.
Clean up the messes, meaning?
Think of it this way. Each process is allocated a set of resources when it's created.
Yeah.
Memory, files, access to certain parts of the system. Destroy is like the meticulous librarian who makes sure everything is returned to its rightful place, ensuring nothing is left out of order.
And what about those family ties you mentioned? What happens to child processes when a parent process is terminated? We don't want any digital orphans running around.
This is where things get really, really clever.
Okay.
Destroy has this built-in mechanism to handle this. It works recursively, meaning if a parent process is terminated, it automatically takes care of all its descendants, ensuring that no process is left behind in a digital limbo.
Wow. So there's a whole unseen world of order and complexity happening every time we interact with our computers. But why should all this matter to the average user?
Well, this elegant system is the reason why you can listen to music, browse the web, and edit documents all at the same time
Right.
without your computer collapsing in on itself.
So it's all about efficiency.
Efficiency and security. But keeping processes isolated, it's like each one operates in its own little sandbox. If one process crashes, it doesn't take the whole system down with it.
Like a digital firewall.
Exactly.
Now that's what I call insightful. So considering the ever-increasing complexity of software and the rise of parallel processing, what's the future of process management? How will it need to evolve to keep pace? Something to ponder. Until next time, keep exploring the fascinating world beneath the surface of your digital life. All right, everyone, ready to dive deep? Today, we're all about operating systems.
But don't worry, we're not getting bogged down with definitions.
No way. We're going way past that. Think how your computer actually juggles everything you throw at it at once.
That's right. The heart of it all.
Yeah.
Resource management.
And believe me, it's way cooler than it sounds.
It really is.
Yeah.
Most people, they don't even think about what's happening behind the scenes.
It's like magic.
Yeah.
But it's this super intricate dance, right? With the OS making sure everything runs smoothly. Well, most of the time at least.
Most of the time, for sure.
So, about that dance, we went all out, got some killer resources for this one. Articles, diagrams, even code snippets.
All about how operating systems handle those precious resources.
Exactly. And to make this crystal clear, imagine your computer is like a packed restaurant.
Okay, I like where this is going.
You've got hungry customers. Those are your programs all wanting something different.
Right, and a limited menu of ingredients, that's your hardware.
Then there's the head chef, making sure everyone gets fed, no one's waiting forever, the whole place doesn't go crazy, that's your OS.
I love that analogy. And just like a real restaurant, things can get pretty hectic, in the thick of it.
Oh, absolutely. Multiple customers placing orders, some more complex than others.
Exactly. Some just want a quick salad, others a 5-course meal, and you've only got so many cooks, so many ovens.
And that's exactly why getting this whole resource management thing is so important, not just for the OS, but for you.
Oh, 100%.
Think about it. When your computer's lagging, where you get that spinning wheel of doom,
Ugh, the worst.
it's usually because of a resource bottleneck, like too many programs open, or one's hogging all the memory.
Like that giant party coming in, ordering everything on the menu at once.
And the OS is stuck there like, hold on, I only have 2 hands.
Exactly. Chaos in the kitchen. And that's when the OS has to step up, be the manager, the ultimate decision maker.
Has to, right? Otherwise, it's game over.
It needs to allocate those resources like a pro, making sure every program gets what it needs without starving the others out.
A delicate balancing act for sure, but absolutely essential if you want your computer running smooth.
Couldn't have said it better myself.
So how does the OS keep track of it all? We're talking everything here. Keyboard, mouse, RAM, CPU cycles, the works. How does it know what's free and what's taken?
That's where things get really interesting, my friend. The OS has this clever system, uses these data structures to manage it all. And one of the most important, the resource control block, the RCB.
The RCB, okay.
Think of it like a detailed inventory card for every single resource the OS has at its disposal.
So each resource gets its own little ID card. What kind of info are we talking here?
Exactly. Each RCB is packed with vital information about its resource.
Yeah.
Like, it's got the resource description. That's the name tag telling you what it is. Memory, a file on your hard drive, even access to your printer, all meticulously categorized.
So it's not just what the resource is, but also like its status? Is it free or is someone already using it? Like, is that table in our restaurant analogy available, or is there a big reserved sign on it?
You got it. The RCB also includes the state of the resource, whether it's free or currently allocated to a process.
Yeah.
Super important for, avoiding any conflicts. Imagine 2 programs trying to write to the same file at the exact same time.
Talk about a recipe for disaster.
Total disaster. So that state info in the RCB, that's like the traffic signal. It makes sure only one program has access at any given time. Keeps things running smooth.
Okay, this is making a lot more sense now. Each resource, it's got its RCB, its information hub. But what happens when a program needs to use one of these resources? How does it actually get its digital hands on it?
That is where the request and release mechanisms enter the picture.
Request and release sounds a little formal, don't you think? For something my computer's doing a million times a second.
Oh, there's going to be some kind of system.
Right.
Yeah.
So how does a program even ask for what it needs?
Okay, let's say a program wants to save some data to your hard drive.
Okay, it makes sense.
Now, it can't just start throwing data around like a digital anarchist.
Definitely not. Data chaos.
It's got to ask the OS nicely. And it does this through, you guessed it, a request function. Sends a little request up the chain saying, hey, I need this specific resource, please.
So the program sends up a flare. Hard drive access needed over here. Then what? Does the OS just hand it over?
Not quite. Remember those RCBs we talked about? The meticulous inventory cards?
Right, for every resource.
The OS is like a librarian, a very meticulous librarian, and checks the RCB for that hard drive, sees if it's available. If it's marked free, meaning no other program's using it.
It's a free-for-all.
Well, not quite a free-for-all. The OS updates its state to allocated, puts a little checked-out slip on it, reserving it for that program.
Got it. So the program gets the green light, hard drive's all theirs. But what if another program needs the hard drive at the same time? Is it stuck waiting?
Absolutely. Yeah. And this is where it gets even cooler. The OS, it doesn't just leave that program hanging.
That would be rude.
Right. It uses something called a waiting list. Basically a queue for programs that need a specific resource.
Like a digital waiting room, full of impatient programs. So how does the OS decide who goes first when the resource is free? First come, first served.
That's where the OS pulls out its secret weapon, the scheduler.
Ooh, the scheduler.
Think of it as the ultimate traffic cop, right? Directing traffic, making sure everything runs smoothly. It uses these algorithms to determine which program gets access next.
Algorithms. Okay, now we're getting serious. So it's not just random. What goes into the scheduler's decision-making?
Oh, it's definitely not random. The scheduler looks at a bunch of things, like how long has each program been waiting, what's the priority level of each program, even how much of the resource each one needs. It's all about efficiency.
Priority level. So some programs are more important. Do I need to start ranking my apps, giving them VIP status?
Uh-huh. You don't have to go that far. The OS has its own system for figuring that out.
Okay, good to know.
Like essential system processes, the ones keeping your whole computer running.
Right. Those seem pretty important.
They're usually higher priority. You wouldn't want your entire system crashing just because you're waiting for, say, a game to load.
Yeah, priorities. Makes sense. But I need an example. How does this priority system actually play out in the real world?
Okay, picture this. You're editing a video, right?
Okay, I'm with you.
But you're also on a video call and maybe browsing the web a bit.
Multitasking, the modern way.
Exactly. Each of those programs needs resources, right?
Yeah.
CPU, memory, network bandwidth.
Got it.
The scheduler's job is to allocate those resources so everything runs smoothly. It's juggling, keeping all the balls in the air.
So how does prioritizing actually work in this scenario?
Well, in this case, the OS might prioritize that video call. Real-time communication is pretty important.
Don't want to miss a thing.
Exactly.
Yeah.
So it would allocate more CPU cycles, more bandwidth to the call, making sure your conversation is clear, no interruptions.
Makes sense. What about those other programs, though? The video editing, the web browsing, just twiddling their thumbs?
They have to wait their turn, but it's usually so fast you don't even notice.
Really?
The scheduler is lightning fast, making these decisions, switching between programs thousands of times every second.
Wow. We are so clueless. It's doing all this, and we just have no idea. Okay, so we've covered how programs ask for resources, the waiting game if a resource is busy, and how the scheduler is the boss of it all. But what happens when a program's done using something?
That's where the release function comes in. It's all about making sure those resources are used efficiently. No bottlenecks.
Release, is that like hitting send on an email? I'm done here, OS. You take it from here.
Perfect analogy. When a program's done, say it's finished with that hard drive, it sends a little signal to the OS.
Like a, hey, I'm good, thanks.
Exactly. That's the release function doing its thing. Basically saying, okay, done with this, you can release it back into the wild.
Back into the wild, love it. No more digital fences around that part of the hard drive. But what does the OS even do with it? That free resource, just sitting there.
Well, remember our trusty RCBs, our little inventory cards.
Always, can't forget those.
The second that program releases the resource, the OS jumps into action, updates that RCB, changes the state from allocated back to free. Now everyone knows it's up for grabs, like taking down that reserved sign at the restaurant.
Queuable for one coming up. So the resource is back in the game. But what about all those programs we left hanging in the waiting list, all queued up? What happens to them?
This is where the OS really earns its stripes, shows off those management skills, immediately checks the waiting list for that resource. And if there are programs waiting...
Showtime.
Right. The scheduler steps up again. Like, all right, who's next? Like a maitre d' who knows exactly who's been waiting the longest, who might be a VIP.
Got to keep things moving, keep everyone happy. So the scheduler analyzes them all, picks the next one in line, based on all those factors. Priority, wait time, all that.
Precisely. And again, this is all happening in the background, instantly. 1 second a resource is busy, the next it's free and already being handed off to another program. The OS is like a ninja.
Seriously, that is amazing. A never-ending dance of requests, releases, allocations, and we're just blissfully unaware.
That's the beauty of a good operating system. All this complexity handled behind the scenes, so we, the users, can just do our thing.
Whether it's editing videos, chatting with friends, exploring the internet.
Exactly. It's like having a super efficient assistant who takes care of everything, no questions asked.
This deep dive has honestly changed how I see my computer. It's not just this magical box anymore. There's a whole system working hard in there.
Glad to hear it. It's like anything else. Once you understand the basics, even just a little, it's not so mysterious anymore. And you can actually use that knowledge to troubleshoot if things go wrong.
For sure. So to wrap up our deep dive into operating systems and resource management, we've learned the OS is like an orchestra conductor, keeping this whole symphony of resources in check.
We saw how the OS keeps track of everything, how programs ask for and give back resources, and the scheduler. That's the real MVP, keeping everything organized.
Absolutely. And hey, maybe this sparks some questions like we talked about the scheduler, how it prioritizes, but can you influence that? Give a certain program a boost, something to ponder. That's all for today's deep dive. Until next time, happy computing.
Ever fire up like a million things on your computer at the same time?
Yeah.
Like you're streaming a movie, playing a game, got a video call going and your computer just handles it.
Happens to me all the time.
Right. So today, we're diving deep into the magic that makes that possible: threads. We've got this awesome excerpt from Paste in Text, and we're going to break it down.
Love this stuff. Threads are the real MVPs behind multitasking.
For real. But what actually are they? Let's say you've got a single core processor. It can basically only do one thing at a time.
Right. Like way back in the day. One program at a time, that's it.
Exactly. So imagine your computer's like a chef with only one pair of hands. They can only chop veggies or stir the sauce, not both at once. That's where threads swoop in.
It's like suddenly giving that chef, multiple sets of hands, can do a bunch of tasks in the same kitchen, same time.
Threads let your computer pretend it has multiple brains, even with just one processor.
Yeah.
So it can switch between tasks super fast, giving the illusion of doing everything at once.
And the key here is efficiency. Threads share the same resources, the computer's memory, the code, everything. Creating a new process for every single little task would be a huge resource hog.
Right. It's way more efficient to have our multi-handed chef than a whole separate kitchen for each dish.
Yeah.
Okay, so there's this awesome example in pasted text. Let me find it. Okay, here we go. Imagine you're browsing the web and a page is loading.
Love a good web analogy.
Me too. Okay,
Yeah.
so the page is loading, right? And while it's fetching the text and stuff, it's also downloading images. Those are probably happening on separate threads. Or when your word processor is spell checking as you type.
Another thread doing its thing in the background.
Exactly.
Yeah.
Okay, so we've got all these threads running around, making our lives easier. But how do they each know what they're doing? Isn't it chaos in there?
Total chaos without the thread control block, the TCB.
The TCB. Sounds kind of ominous, like the Thread Censorship Bureau.
Definitely not that. Think of it like each thread's personal little to-do list. It's got all the essential info, where the thread left off, what data it needs, where to put the results. Keeps everything organized.
So it's like each of our multi-handed chef's hands has its own little recipe card. Makes sense.
Exactly. Keeps everything running smoothly.
Now, here's where it gets really interesting. We've got these different ways to manage all these threads. User level versus kernel level threads.
Right, it's like who's in charge of the kitchen staff. With user-level threads, the application itself calls the shots. It's like a small, independent restaurant where the head chef manages everything.
Keeps it nice and simple.
Exactly. It's fast, flexible, and portable. But here's the thing. If one thread messes up, let's say it crashes, the whole application can go down with it.
Oh no, everything comes to a screeching halt.
Yep. One chef drops a tray, and suddenly, everyone's waiting.
Not ideal. Okay, so what about kernel-level threads?
Kernel-level threads are like having a restaurant owner who oversees everything. The operating system itself manages the threads directly.
So there's more oversight.
Right. It's a bit more resource-intensive, like having a manager on the payroll, but it's way more robust. If one thread crashes, the others can keep chugging along. Plus, you can take advantage of multiple processors.
Like having multiple kitchens.
Exactly. You can really maximize your efficiency.
So how do developers choose? Is it like ULTs for simple stuff, KLTs for more intense things?
Pretty much. BLTs are great for small, single-core tasks, simple text editors. KLTs shine with video editing, 3D rendering, anything that needs raw power and can use all those processors.
Gotcha. So with most things in tech, there's no one-size-fits-all. Depends on the recipe.
Absolutely. And the cool thing is, a lot of modern operating systems, they're clever. They'll use a combination of ULTs and KLTs.
Best of both worlds.
Totally. Super efficient threads managed by the application, but then they're mapped onto a smaller number of kernel threads for that extra stability.
It's like having sous chefs who report to the head chef,
Yeah.
who then reports to the owner. Everyone's got their role.
Perfect analogy, and it really highlights how much thought goes into software design.
Right. We never even think about this stuff.
Yeah.
But it's the reason our computers can handle our entire digital lives.
Exactly. And it makes you wonder, with all the crazy advancements coming up, quantum computing, AI chips, how will we manage threads in those systems? What will the future of multitasking look like?
Right. We're already juggling a million things. Imagine what it'll be like in 10 years.
It's going to be wild.
Wild indeed. Well, there you have it, folks. A deep dive into the world of threads. Next time your computer's humming along, juggling your tasks like a pro, you'll know the secret's out. It's all thanks to threads. Ever find yourself juggling a dozen tabs, streaming music, and then, also trying to edit a photo all while your computer somehow keeps up? It's like a magic act, right?
Right.
Well, today's deep dive is all about that hidden language that makes this whole digital juggling act possible, interprocess communication, or IPC for short. Our listener sent over this fascinating snippet on IPC from what looks like an operating systems textbook. Clearly, someone's been hitting the books, right? And you know what? After reading this, I have to say, the stuff going on under the hood of our devices, it's way more interesting than I ever gave it credit for. So imagine this. Different programs running on your computer. They're like chefs in this bustling restaurant kitchen. Each chef has, their own specialty, their own station. But to get that delicious meal on your table, or that amazing website on your screen in this case, they need to be able to communicate and coordinate like crazy. And that is where IPC comes in. Now, our source text, it gets into like the nitty-gritty of how this communication actually happens, talking about things like shared memory and message passing. It's a little bit like comparing walkie-talkies to like a shared bulletin board, different tools for different jobs, right? But before we dive into those details, I'm kind of curious to get our experts' take on the bigger picture here. Like, what's the why? Why is this hidden language so important?
Well, I think what's really fascinating here is that ITC is all about making your computer not just, functional, but actually efficient and enjoyable to use. Think about it without IPC, like just opening a new tab in your browser could be as slow as like booting up your entire computer back in the 90s.
Oh, the days of staring at the hourglass. Thankfully, we've evolved.
Exactly. And our source text breaks down the why into like a few key points. And I think the most relatable one is speed. By, breaking down tasks and allowing different programs to run parts of them simultaneously. IPC really supercharges your computer's processing power. It's like having a team of chefs instead of just one thing's just move much faster, right? But it's not just about speed. Remember that whole modularity idea from the text? That's huge too. IPC, it lets developers build programs kind of like Lego blocks, Each one is self-contained, but they're able to connect with others. This makes software more robust and way easier to update too. You can just swap out a faulty Lego block without bringing down the entire creation.
Okay, so it's like if one chef in our kitchen makes a mistake with the soup, we don't have to shut down the entire restaurant, right? We can just fix the soup and keep things moving. Makes sense.
Precisely. And that actually brings us to a perfect example from your source material, the Chrome browser.
Chrome. Okay, so we use it every day, but honestly, I never really stopped to think about what's going on, beneath the surface. What makes Chrome such a prime example of IPC in action?
Well, think about how you typically use your browser, right? You've got, multiple tabs open. Maybe you're reading an article, watching a video, checking your email, all at the same time. Each of those tabs, that represents a separate process doing its own thing.
Okay, so it's like each tab is its own little independent chef in our restaurant kitchen analogy.
Exactly. Each one has, its own resources, its own memory space, and they're all running concurrently. Now, in the past, if one website crashed, it could take down your entire browser. Imagine if one chef using a faulty stove brought the whole kitchen to a standstill.
Oh, tell me about it.
Yeah.
I've lost count of how many times I've had to start over because one pesky tab crashed.
Yeah.
Not a fun experience. So how does Chrome prevent that from happening?
So Chrome's multi-process architecture, it's actually designed to isolate these processes. It's like each chef has their own separate mini kitchen. So if one has a mishap, it doesn't affect the others.
That is such a good analogy. So if one website crashes, it's only that tab that's affected. The other tabs in the main browser process, they remain, unscathed. Brilliant. But how do these separate tabs or mini kitchens, how do they actually share information when they need to? That's where shared memory and message passing come in.
You got it. Remember the walkie-talkies and the bulletin board? Shared memory, it's like that bulletin board where processes can post and grab information really quickly. It's super efficient for large amounts of data. For example, if two tabs need to access the same images or files.
Makes sense. But our source material did mention some potential downsides to shared memory. Something about things getting messy.
Right. The downside is that it can lead to what we call race conditions. Imagine two chefs trying to grab the same ingredient from the pantry at the exact same time. With shared memory, multiple processes can access and modify data simultaneously, and that can cause conflicts if they're not careful.
So it's fast, but potentially chaotic.
Yeah.
What about message passing? That's where the walkie-talkies come in, right?
Exactly. Message passing that's much more controlled. It's like the chefs are sending messages to each other through, a reliable system. It might be a bit slower than shared memory, but it ensures that that the processes don't kind of trip over each other when they're trying to access or modify data.
So it's hey, I need that ingredient. Can you send it over when you're done? Much more organized.
Precisely. And the source text mentions another crucial aspect of this, the sandbox. It's like each mini kitchen also has its own security guard, making sure that a problem in one place doesn't spread to the others.
Okay, so a sandbox is like a safety net, preventing a malicious website from affecting like other tabs or my entire system. That's reassuring.
Exactly. It adds another layer of protection, ensuring that, even if one tab is compromised, the damage is contained.
This is all making so much sense now, like it just all clicks into place.
Mm-hmm.
So we've got shared memory that's our, speedy but potentially chaotic bulletin board. And then we've got message passing, our more controlled but maybe a little slower walkie-talkie system. Given like those trade-offs, how do operating systems decide which one to actually use? It feels like there must be times when one is just a way better fit than the other.
Oh, you're absolutely right. Yeah, it's just definitely not a one-size-fits-all kind of situation. Think of it this way: if you're dealing with something like real-time stock market data, where like even a microsecond delay could end up, costing you money. You just need raw speed shared memory. That's the way to go in those cases.
Yeah, it's like our chefs need to know the instant a dish is like, sold out so they can start prepping more. Like there's no time to like send a message. They just need to see that order queue.
Exactly. But then on the flip side, imagine you're dealing with something like online banking, right? Speed is still important there, but security, that's like absolutely paramount in that case. That's where that controlled step-by-step nature of message passing, that's where it really shines.
Yeah, it's like setting those transactions in an armored truck, right? Instead of just like shouting them across the kitchen. This has been an incredible deep dive, really eye-opening stuff. I used to think of my computer as like this mysterious black box, but now I'm starting to see like the elegance of all this communication that's happening behind the scenes. What would you say is like the biggest challenge when it comes to keeping all these processes talking smoothly and and securely?
That's a great question to end on, actually. I think the biggest challenge is it's kind of finding that sweet spot, right? That sweet spot between security and efficiency. As we rely more and more on interconnected devices and systems, that balancing act, it's only going to get tougher, right? How do we keep things, fast and seamless for the user without compromising on security in a world where data is becoming, it's already valuable. It's only becoming more valuable.
It really makes you appreciate that invisible world, right? The world of software and operating systems all working tirelessly behind the scenes so we can, binge watch our shows and scroll through social media without even a second thought. So next time your device is doing that whole digital juggling act, breaking a sweat, take a moment to appreciate the unsung hero, interprocess communication. It's a silent symphony that keeps our digital world humming along in perfect harmony.
Okay, so picture this. You're in a crazy busy restaurant kitchen, right? Chefs are flying around totally in the zone, dish after dish.
Yeah, smells amazing, right?
Oh, absolutely. But on the other side, you've got these hungry diners like super eager for their food. So what's the key to keeping everything running smoothly?
Coordination is absolutely key. It's all about timing.
Right. And that's basically what this whole producer-consumer problem is all about in computer science, isn't it?
It really is. It's this fundamental idea that makes sure different parts of a system can work together, like seamlessly, even when they're doing totally different tasks at the same time.
Like a perfectly choreographed dance, but with data. And in our deep dive today, we're going to unpack how shared memory makes this intricate dance possible. So help us out here. What does shared memory actually mean in this whole context?
Okay, imagine a central bulletin board, right?
Yeah.
But this isn't just any bulletin board. This is a bulletin board that all the different parts of a system can access.
Okay, I like where this is going.
Yeah, so instead of passing messages back and forth,
Yeah.
like constantly, which by the way can be a really slow and error-prone process, they've got this shared space to communicate directly. Efficiency is key, right?
Okay, I'm with you. Digital bulletin board for data. I like it. But like, what happens if the board gets overloaded? Like, what if you have a chef who's just cranking out dishes way faster than the servers can deliver them?
Such a good question.
Yeah.
And this is where the concept of bounded versus unbounded buffers comes into play.
All right, break those terms down for us. What's the difference?
Okay, so think of it this way, a bounded buffer. It's like a restaurant with a limited number of tables. If every table's full, the chef has to wait for one to open up before they can serve the next dish.
Makes sense.
Right. It's about managing those resources carefully. But then you have an unbounded buffer. That's more like, imagine a never-ending buffet line. The chef can keep adding food, and diners might have to wait a bit if the line's long.
Okay, so bounded buffer, great for making sure you've got that predictable memory usage, but our hardworking chef might get put on pause sometimes.
Exactly.
And unbounded, the chef's on fire, but it could gobble up more memory, which isn't always ideal. Fascinating stuff. But let's get down to brass tacks here. How do these buffers actually work in the code itself? Our source material gets into some pretty specific examples using something called a circular array.
Yeah, the circular array, it's a really common way to actually implement this bounded buffer.
Yeah.
Quite elegant. Imagine like a clock face, almost.
Okay, I'm picturing it. What's going on this data clock?
So we've got these 2 pointers, right? Just like the hands on a clock, we call them in and out.
Okay.
In, that pointer keeps track of where the next piece of data should be written to. Like, think of it as the chef placing a dish on the buffet.
Gotcha.
The out pointer, that marks the spot where the next piece of data should be read from. It's like the diner picking up their meal. And as the buffer fills up, these pointers move around the clock face, ensuring you're not overwriting data that hasn't been consumed yet. Keeps things flowing.
So the in pointer is constantly chasing the out pointer around the clock, but because it's circular, they never actually collide and mess up the data. Pretty clever.
Exactly. That's exactly it. And this clever design is what keeps everything running smoothly in the background. It's ensuring your video plays without a hitch, that your document opens without any corrupted text. It's all about maintaining order in this digital world.
Okay, this is making perfect sense, but this brings up kind of a crucial question for me. What's stopping our chef and diner from bumping into each other at the buffet if they both reach for the same spot at the same time, in that shared memory space?
Oh, you're touching on a critical point, and it's something that often trips people up, especially when they're first wrapping their heads around all of this. The code example we're looking at, it focuses on the structure of the buffer itself, but it doesn't explicitly address how to prevent those potential collisions you're talking about.
Data chaos. So it sounds like we need some serious traffic control to keep things running smoothly in our digital kitchen here.
Exactly. And that's where synchronization mechanisms come in. Now, without getting too bogged down in the technical details, these mechanisms are basically like traffic signals at a busy intersection. They make sure that only one process, either the producer or the consumer, can access the shared memory buffer at any given time.
Okay, so we've got our shared memory space, our super clever circular buffer, and then our traffic signals to keep everything in order. That's amazing. But how does this all connect to the bigger picture? I mean, this might seem like a very specific coding problem.
Yeah, and you might be wondering, how does this apply to me? But I can assure you, this producer-consumer model, it's everywhere in computing. Think about a web server, responding to a ton of requests from users who are browsing the internet.
Oh, I see. So the web server is like our superstar chef, just churning out web pages as fast as possible. And the users are like those hungry diners, all requesting different dishes, or in this case, web pages at the same time.
Precisely. Or consider a compiler. It takes your code, breaks it down, and then generates those instructions for the computer to actually execute. The different stages of compilation, things like turning your code into assembly language and then into machine code, they act as producers and consumers, passing data along in a very orderly fashion.
Wow, I never realized how much thought goes into something as simple as opening a document or loading a web page. It's all thanks to this elegant solution to the producer-consumer problem happening behind the scenes. This deep dive is already blowing my mind, and we're just getting started. So what you're saying is this, seemingly abstract concept, it's actually the backbone of so many digital experiences we just, totally take for granted. That's wild.
It really is. And, it's not just things like web browsing or opening up a document. Remember those streaming services you use?
Oh, yeah, of course.
Imagine watching your favorite show, and every few seconds, bam, it pauses to buffer.
The worst.
Right. Especially when you're at the good part.
Totally.
A well-implemented producer-consumer solution, that's what prevents that from happening. The producer, in this case, would be the part of the system that's downloading the video data, and the consumer is the part that's playing it back on your screen, right?
Right.
They work in perfect sync, and it's all thanks to those shared memory buffers we were talking about. Smooth playback.
Got it. That makes sense. But you mentioned race conditions earlier. What happens if those synchronization mechanisms, they fail? And our chef and diner try to access the buffet at the exact same time.
Yes. Race conditions, the bane of many a programmer's existence.
I bet.
Imagine 2 chefs trying to put dishes on the same spot on the buffet at the exact same time. What do you think's going to happen?
Total chaos. Spilled food, broken plates, hurt feelings, probably.
Exactly. A recipe for disaster. In the world of data, a race condition could lead to corrupted files, maybe even system crashes, or even worse, security vulnerabilities.
Yikes.
Those synchronization mechanisms, those traffic signals, they are crucial for preventing these digital disasters.
Right, so it's not just enough to have the shared memory and the buffer. You've got to have those traffic signals in there directing the flow and keeping things running smoothly.
Exactly. And this is where things get even more interesting because developers have to make choices about what kind of buffer to use, bounded or unbounded, and which synchronization mechanisms are going to work best for their specific application.
So it's like choosing the right tool for the job.
Exactly. There's no one-size-fits-all here. For example, imagine you're designing a system for high-frequency trading platform, where every microsecond counts.
Oh, yeah. High stakes.
Right. In that scenario, you're probably going to prioritize speed above all else. You might go for an unbounded buffer to make sure that the producer, the part that's receiving that real-time market data, never has to wait, even if it means using up a bit more memory.
Yeah, because in that world, even a millisecond delay could be the difference between, like, making a fortune and missing out, right?
Absolutely. But now let's say you're designing a system for, like, a medical device where data integrity is absolutely critical.
Right, okay. Got to be extra cautious there.
Exactly. In that situation, you might choose a bounded buffer, even if it means the producer has to pause occasionally.
Interesting.
It's all about finding that right balance between performance and how you're managing those precious resources, depending on what the application actually needs.
It's crazy to think about all these different factors that developers have to consider when they're building the systems that we use every day.
It really is. And this producer-consumer problem, it might seem kind of niche at first, but it highlights something really fundamental about computer science. It's not just about writing code. It's about solving problems, managing those resources, and just making sure those digital chefs and diners can keep cooking and enjoying their meals without a hitch.
It's kind of mind-blowing when you really think about it, know? This whole hidden world of digital chefs and diners all perfectly in sync just to give us these seamless experiences we totally take for granted.
It really is. It speaks to how amazing these computer scientists and programmers are, finding these elegant solutions to such complex problems like this whole producer-consumer thing.
This deep dive has been, honestly, super eye-opening. Before we wrap up, though, any final takeaways? Like a nugget of wisdom you can leave our listeners with? Something to ponder, when they're firing up their favorite app or streaming their next movie?
Absolutely. So next time you're on your computer or your phone, right, just take a second. Think about that intricate dance of producers and consumers going on behind the scenes.
Yeah, I'm going to be seeing it everywhere now.
That smooth video playback, that seamless file download, even just typing an email, all of it. It's only possible because of these incredibly well-designed systems working tirelessly to keep everything in sync.
Wow, a whole new level of appreciation for the tech we use every day.
Exactly. Even understanding just the basics of how these systems work, I think it gives you this whole new perspective on the digital world around us.
It definitely has for me. This has been such a cool journey into the heart of the producer-consumer problem. Thank you so much for, guiding us through it.
Oh, my pleasure.
Yeah.
Always happy to nerd out about this stuff.
And to all our listeners out there, we hope you've enjoyed this deep dive as much as we have. Until next time, keep exploring, keep those questions coming, and keep marveling at just how incredible the digital age really is. Ever try to picture something as complex as an operating system? Like coordinating a million chefs in a kitchen, each with their own recipe, but they've got to work together to make a single dish.
That's a pretty good analogy, and that's where inter-process communication comes in, or IPC for short. It's really the heart of how things get done at computers.
And today we are serving up a deep dive into one flavor of IPC called message passing. We'll be working with excerpts from an operating systems textbook to, really break down this fundamental concept. By the end, you'll understand how different parts of a computer, even a whole network, can work together smoothly.
Yeah, we'll get into the nitty-gritty of why that's so crucial for everything from apps on your phone to the internet itself.
Our source material starts by introducing processes. Think of them as those chefs in our analogy. Each one is an independent program running specific tasks within your computer.
Exactly. And much like chefs need to coordinate, share ingredients, and basically not crash into each other in a busy kitchen,
Right.
processes need to communicate effectively.
Right.
But there's a catch.
There's always a catch, isn't there?
Well, in this case, it's that processes often don't have direct access to each other's memory space.
Yeah.
It's like each chef having their own separate set of ingredients that they can't just grab from, willy-nilly.
Okay, so no swiping a whisk mid-mix.
Exactly.
So how do these processes manage to share information and work together without, like, stepping on each other's digital toes?
That's where message passing comes in. Instead of directly grabbing what they need, processes send these carefully prepared packages of data. Those are the messages back and forth.
So it's like they're sending ingredients between stations with specific instructions.
Yes.
I need 2 cups of flour, stat.
You got it. And this becomes even more important in systems spread across multiple computers and the internet, massive databases, or even just your phone talking to a server.
Right, because things are getting done all over the place.
Yeah.
Now, if we think about how these messages are sent, is there like a standard size? Or can a process send a small request or a whole recipe book's worth of data? So we've got these processes sending all these messages, big and small. But how do they actually make sure those messages are getting to the right place? Is it like direct messaging or more like sending a postcard?
That's a great question. It gets to the heart of how message passing is structured.
Yeah.
See, our textbook talks about 2 main ways processes communicate: direct and indirect communication.
Okay, let's start with direct communication. It sounds, well, pretty self-explanatory.
It is, in a way. Think of like having someone's direct phone number. If you want to send them a message, you just dial the number. In direct communication, a process needs to know the exact identifier of the process it wants to talk to.
So kind of like knowing a computer's specific IP address on a network.
Exactly. And just like with phone numbers, if that address changes, you're out of luck. Our textbook points out that this method, while simple, can be a real headache in large systems where things are changing dynamically.
Yeah, that sounds like a recipe for disaster, especially with millions of processes potentially needing to communicate. So how does indirect communication make things more flexible?
Well, instead of relying on knowing each other's constantly changing addresses, indirect communication uses something like a shared mailbox.
Okay, so more like emailing than making a phone call.
Perfect analogy. In this model, processes send their messages to these designated mailboxes. Any process with access to that mailbox can pick up messages regardless of who sent them.
I can see how that would simplify things. But what's stopping messages from getting lost or mixed up if multiple processes are using the same mailbox? I mean, that sounds like my inbox during peak spam season.
Now you're thinking like a computer scientist. Our textbook dives into this very issue, and it's a critical one. Managing these shared mailboxes effectively is essential. Think of it like a group project where everyone's supposed to drop their contributions in a shared folder. Without clear rules and organization, it'd be chaos.
Been there, felt the chaos of a disorganized group project.
Yep.
So how do computers keep their digital messages from turning into a jumbled mess?
This is where the concept of synchronization enters the scene. And our textbook highlights this by contrasting 2 key approaches: blocking and non-blocking operations.
Okay, those sound a little intimidating. Can you break them down?
Absolutely. Imagine sending a text message. With a blocking send, you hit send and wait, glued to your phone until the other person reads your message. You're essentially blocked from doing anything else until you get that notification.
I think we've all been there. Sometimes you need that instant gratification of knowing your message was received. But what about non-blocking? It sounds a bit more, I don't know, carefree.
Exactly. With a non-blocking send, you fire off that text and immediately move on with your day. You're not waiting around for a response. You might not even know if or when the message is read.
So it's the difference between needing a reply right away and being okay with the message getting there eventually. I can see how both would be useful depending on the situation. But how does this play out in the world of message passing between processes?
Imagine a process that's constantly churning out data. We'll call it the producer. Now let's say there's another process, the consumer, that needs to take that data and do something with it. If the producer uses a blocking send, it's stuck waiting until that consumer is ready to receive.
That sounds like it could really slow things down if the consumer is busy, like waiting for someone to finish using the only copy machine.
Exactly. Now, if the producer uses a non-blocking send, it can keep generating data without waiting. But now the consumer needs a way to manage this incoming data flow. This is where buffering steps in. Think of it as a waiting area for messages.
Buffering? Is that like when I'm trying to stream a movie and it pauses to load? It's incredibly annoying.
You got it. That buffering is your computer creating a temporary storage space to manage that incoming data stream from the internet. Our textbook breaks down buffering into 3 main types: zero capacity, bounded capacity, and unbounded capacity.
Yeah, okay, I'm intrigued. Let's unpack these different buffer types. Starting with zero capacity, what does that even mean?
Zero capacity is the strictest kind of buffer, or rather the lack of one. Imagine a restaurant with no waiting area whatsoever. If someone arrives and there's no table ready, they're out of luck. Similarly, with a zero-capacity buffer, if a message arrives and the recipient isn't ready, the sender has to wait.
So very efficient if everything is perfectly timed, but not very forgiving in the real world. What about bounded capacity? That sounds a bit more realistic.
It is. Think of it like a restaurant with a limited number of seats in the waiting area. Things run smoothly until every seat is taken. Then, new arrivals have to wait their turn. A bounded capacity buffer works the same way. It has a fixed size, and once it's full, new messages have to wait until there's space.
Ah, the digital equivalent of taking a number and waiting for your turn. And that leaves us with unbounded capacity, which I'm guessing is the dream scenario.
You could say that. Unbounded capacity is like having a magical waiting area that never gets full. There's always room for one more message. While this sounds ideal in theory, in reality it could lead to problems if the inflow of messages outpaces the system's ability to process them.
Right, like an ever-growing to-do list that never actually gets shorter. So there are trade-offs with each buffering approach. It seems message passing is all about finding that sweet spot between efficiency, flexibility, and managing resources effectively.
You've hit the nail on the head. There's no one-size-fits-all solution. Choosing the right approach depends on the specific needs of the system and the types of communication happening.
So from direct and indirect communication to that nail-biting suspense of blocking versus non-blocking, and even a trip to the digital waiting rooms of buffering systems, we've really covered a lot.
It's quite a lot to digest.
Yeah.
But as you can see, message passing is this delicate dance of strategies, all working behind the scenes to keep our digital conversations flowing.
Yeah, it really highlights just how much complexity is like hidden beneath the surface of the technology that, we use every single day.
Absolutely. Each of these concepts, from the simplicity of direct communication to those intricate buffering systems, they all play a crucial role in making sure your computer can handle, well, everything you throw at it.
It really is amazing how these concepts, which sound pretty abstract at first, actually mirror real-world situations so closely.
That's the beauty of computer science, right? It's all about finding those elegant solutions to these complex problems, often by, drawing inspiration from the world around us.
Speaking of real-world parallels, it makes me think about how we communicate as humans, our inboxes, for example. Do you think they function more like a bounded or unbounded buffer?
Ooh, that's a fascinating question. I mean, on one hand, our inboxes seem unbounded. We can receive practically limitless emails, right? But then in reality, there are limits to storage space. And we often create our own boundaries with like folders and filters.
It's almost like we instinctively try to impose some order on that potential chaos of an unbounded data stream.
It speaks to a fundamental need for, structure and organization in how we manage information, even in this digital realm.
So much of our communication today is asynchronous, sending emails, texts, or messages, and not really expecting an immediate response. Do you think this shift towards more kind of non-blocking communication is changing how we connect with each other?
That's a profound question, and it has no easy answers.
Oh.
On one hand, asynchronous communication allows for flexibility and efficiency. Right? We can respond to messages on our own time, juggle multiple conversations, and connect with people across, different time zones.
But I do wonder, does it also create a sense of constant low-level anxiety, like this expectation that we should always be reachable, always be responsive?
It's a delicate balance. And finding that sweet spot between staying connected and managing, the constant flow of these digital interactions, it's an ongoing challenge for all of us.
It certainly is something to think about as we all become increasingly reliant on these asynchronous communication tools.
Indeed. And by, understanding these underlying concepts of message passing, I think you're better equipped to navigate these complexities of our, increasingly interconnected world.
Well, there you have it. A deep dive into the fascinating, complex world of inter-process communication.
Yeah.
We journeyed from the bustling kitchens of our computer systems to the philosophical implications of how we communicate in the digital age.
Absolutely.
We hope this episode has given you a new appreciation for the intricate dance of messages that keep our digital lives running smoothly.
Yep.
And hey, maybe the next time you hit send on an email or see that dreaded buffering message on your screen, you'll have a little more insight into this hidden world of communication happening behind the scenes.
Until next time.
From all of us here at The Deep Dive, thanks for listening. Hey everyone, and welcome back. Ready to dive into another tech deep dive?
Absolutely. Let's get into it.
Today we're tackling a topic that's, well, kind of hidden beneath the surface of what we usually talk about.
Yeah, it's inter-process communication. IPC for short.
Right, IPC. We got a ton of great excerpts from you all on this one, focusing on how different software components actually talk to each other. It's something we take for granted every time we use our computers, but those conversations are happening constantly in the background.
And they can be surprisingly complex.
Yep.
Which is why we are not just going to lay out what the different IPC methods are, but really get into the why behind those choices.
Exactly. So, to set the scene, we're mainly digging into a text on operating systems. Think of it like getting a behind-the-scenes tour of your computer.
We're talking about 4 main players in the world of IPC. Good old pipes. Then P06 shared memory, the always interesting mock message passing, and finally, how Windows tackles things with ALPC.
And just a heads up for our listeners, we're going to jump between these a bit to show how they build on each other. Yeah.
Exactly. Makes more sense to see the evolution of these ideas than just list them out.
Perfect. So kicking us off, the OG of IPC pipes. I always picture this one like the plumbing of an operating system, just creating those channels for info to flow.
Right. Simple but effective. It's a one-way street for data between processes. And remember, a process is basically just an app or program running on your computer.
Now, I know from the excerpts that there are actually 2 types of pipes, right? Ordinary and,
Named pipes. Yeah, the ordinary ones are temporary, like for when you just need to pass some quick info between processes. The named pipes stick around a bit longer and can even be accessed by multiple processes.
That rings a bell. The Windows examples you share really showed how that can get kind of hairy to manage when you've got a bunch of processes all trying to use the same named pipe.
Oh, for sure. It's like trying to direct traffic at rush hour. You need clear rules and mechanisms in place to prevent any collisions and make sure the data goes where it's supposed to.
Makes sense. So to sum up, temporary pipes for quick chats, named pipes for when multiple processes need to get in on the conversation. When would you actually use one over the other in real life, though?
Okay, so imagine you're streaming a movie. That data flowing from Netflix or whatever to your media player that could easily be handled by an ordinary pipe, that temporary connection.
Okay, that tracks.
But now, say you've got a printer, right? And it's got to handle documents from all sorts of apps on your computer. That's where a named pipe steps in it, acts like a central hub, collecting all those print jobs and feeding them to the printer in a nice orderly fashion.
Gotcha. So it's like a much more organized way to handle multiple inputs at once.
Precisely.
Fascinating stuff. So we've got these pipes moving data around, but things start to get really interesting when we talk about P06 shared memory. This one's less about sending messages back and forth and more like everyone's working off the same whiteboard at the same time, right?
Perfect analogy. With shared memory, you've got multiple processes that can all access and, importantly, change the same chunk of memory.
And that's got to be way more efficient for processes that need to be in constant sync, yeah.
Absolutely. Direct access means no middleman, no waiting for messages to go back and forth. But, and this is a big but.
Yeah, what happens if 2 processes get a bit too eager and try to write to the exact same spot at the same time? Seems like you could have a real mess on your hands.
Exactly. That's the risk with shared memory data corruption. It's like 2 people trying to write on the same whiteboard with the same marker at the same time. It's just going to be gibberish.
So how do you avoid that?
Careful coordination. Processes need to use things called synchronization mechanisms. Mutexes and semaphores are the big ones. They basically act like a system for who gets to write to the shared memory at any given time.
So it's like they have to agree on who's holding the marker before anyone starts writing.
Exactly. And that can get pretty complex to manage, especially when you've got a lot of processes vying for their turn. Which is why the next IPC method we'll discuss, mock message passing, is so fascinating. Instead of a free-for-all whiteboard, imagine a super organized mailroom where every piece of mail is carefully addressed and delivered.
Mock. This one's always intrigued me, especially because of its connection to macOS and iOS. So instead of shouting across the shared memory whiteboard, with mock, they're sending each other carefully labeled letters. Tell me more.
You got it. In Mac, it's all about messages. Think of them like self-contained little packages of information.
Okay, I'm picturing those little pneumatic tubes they used to have at the bank.
Yeah, kinda. So each message has got a header like an envelope that tells you who sent it, where it's going, and even how big the message is.
Makes sense. Keeps things organized. But doesn't that add a lot of overhead? I mean, compared to just dumping everything into shared memory?
It does add a bit, yeah. But that overhead comes with some serious perks. Think about Mac OS and iOS. They're known for being pretty snappy, right? That's partly because of Mock. See, this structured messaging, it minimizes errors and keeps everything running smoothly even when you've got tons of apps open.
Okay, that makes sense. So it's prioritizing reliability over raw speed.
Exactly. But here's the thing, Mach isn't just about being organized, it's also got some tricks up its sleeve for efficiency. For example, if a process needs to send a really big chunk of data, instead of making a copy of the whole thing and sending it through a message, it can just send a pointer like directions to where that data lives in memory.
Whoa, that's clever. So instead of sending a whole file, you're just saying, hey, it's over here if you need it.
Exactly. And that can be a huge time saver, especially for things like large images or videos.
So it's like Mach starts with a focus on control and reliability with the whole messaging thing, but then it throws in these efficiency boosts like pointers to keep things speedy.
Exactly. It's all about balance,
Yeah.
right? And that's actually a great segue into how Windows approaches things with ALPC.
Oh, right. ALPC, if I remember correctly, is all about adapting to the situation, right? Like it looks at shared memory and message passing and decides which tool is best for the job.
Nailed it. ALPC. It stands for Advanced Local Procedure Call. By the way, it's all about flexibility. If the processes need to exchange small bits of information, it'll use fast message queues.
Okay, so like those pneumatic tubes we were talking about, right? For those small, quick deliveries.
Right. But for larger chunks of data, it switches gears and uses shared memory to give those processes direct access.
So it's like having a whole fleet of deliver vehicles at its disposal, each optimized for a different kind of package.
I like that analogy. And this adaptability is one of the reasons why Windows can handle such a wide range of applications smoothly. Everything from simple text editing to super demanding games, it tries to pick the most efficient approach for each situation.
Makes perfect sense. Having that flexibility seems crucial for an operating system like Windows that needs to be, well, pretty much everything to everyone.
For sure. And it all comes back to that idea we were talking about with Mach. There's always a trade-off. You're balancing speed and efficiency against things like security and making sure the data doesn't get corrupted.
It's a balancing act, and the choices an operating system makes about IPC have a huge impact on how well it performs, even if we don't always see those choices directly.
100%. And what's so cool is that these choices, they often reflect the overall philosophy of the operating system itself. Like, even though we've been talking about pretty low-level stuff, you can start to see those design decisions reflected in the actual user experience.
It really is amazing when you think about it, all this intricate communication happening behind the scenes, just so we can open a web browser or play a game.
It's like we've been on a little expedition into the inner workings of our computers, and what we found is this incredibly complex, but also really elegant dance of data.
Absolutely. And the more we learn about these IPC methods, the more we start to see how they're not just technical choices, they actually reflect the design philosophy of the entire operating system.
Right. Like with Mach, you can see Apple's emphasis on security and that really tight control over how things work.
Yeah, and then with Windows, you've got this focus on flexibility and being able to handle anything you throw at it, which honestly, given how many different things people use Windows for, it kind of has to.
Exactly. It's all about trade-offs.
Yeah.
And the way an operating system handles IPC is a great example of that.
Yeah.
There's no single right answer. It all depends on what you're optimizing for.
For sure. But okay, I'm going to shift gears a bit here because we've covered a lot of ground, and I always like to leave our listeners with something to think about, connect these ideas to the bigger picture.
I'm all ears.
So we've been talking about how operating systems have evolved different ways for processes to communicate, right? Pipes, shared memory, message passing, all these different tools in the toolbox. But as our devices become more connected, I mean, we're talking Internet of Things, cloud computing, the works, do you think these IPC methods, are they going to be enough? Or do we need totally new ways for all these devices and platforms to talk to each other?
That is such a great question. And honestly, I don't think there's a simple answer. On the one hand, the IPC methods we've discussed, they're already being used in some pretty amazing ways. Like, think about how seamlessly your phone can connect to your car or your smart home devices. A lot of that is built on these fundamental IPC principles. But on the other hand, the sheer scale of interconnectedness we're moving towards, it's unprecedented. So yeah, we're going to need some serious innovation in the world of IPC to handle all that data, all that communication in a way that's both efficient and secure. And the really exciting thing is that this is an area of active research and development. People are working on new IPC methods all the time, trying to push the boundaries of what's possible.
Like, the more connected we become, the more important that underlying communication layer becomes. It's fascinating, and I'm kind of curious to see what the future holds for IPC.
Me too. But for now, I think we've given our listeners a good foundation to understand the basics and maybe even sparked some curiosity to learn more.
Absolutely. So as we wrap up this deep dive into interprocess communication, just remember, folks, the next time you open an app or send a file or even just browse the web, there's a whole lot of communication going on beneath the surface, and now you have a better understanding of how it all works.
And who knows, maybe some of you listening will be the ones developing the next generation of IPC solutions.
That's a great thought to end on. Thanks for joining me for another deep dive.
My pleasure, as always.
And to all our listeners, until next time, keep those curious minds engaged, and we'll catch you on the next deep dive.
All right, so we're diving into multi-core programming today. I know, you hear multi-core and you think, oh boy, back to computer science 101. But trust me, this is going to be way more fun than deciphering binary code.
Yeah, definitely.
We're talking about how computers juggle a million things at once, and more importantly, why you should even care. And luckily, I snagged an expert to help us break it all down.
Happy to be here.
So I was checking out the research you sent over, and one thing really jumped out at me. This whole transition to multi-core, it wasn't exactly a walk in the park for the software folks, was it?
No, not at all. You see, on the surface, going from single-core to multi-core CPUs seems like a no-brainer, right? Like, just add more cores, more power, right?
Right.
But the reality is it threw a massive curveball at programmers. It's like giving you a bunch of amazing ingredients but no recipe.
Okay, I'm intrigued. So it wasn't as simple as build it and they will code. What were some of the biggest hurdles they faced?
Well, for starters, imagine having to chop up a program, something that was designed to run in a nice straight line, and suddenly you have to figure out how to make it dance across multiple cores simultaneously.
Ouch, yeah, that sounds complicated.
It was a huge paradigm shift. Like, imagine trying to split a complex recipe into parts that different cooks could work on at the same time. You'd need to make sure each part made sense on its own, and that they all came together correctly in the end.
And I'm guessing even getting to that point was a challenge in itself.
Exactly. It's not just about dividing the work, it's about managing it effectively across all those cores. Even operating systems, the unsung heroes that keep our computers running, had to evolve to handle this new multi-core world.
Operating systems, the silent puppet masters we never think about until something goes wrong.
Exactly. They had to become expert jugglers, constantly scheduling and directing traffic between cores to prevent any digital fender benders.
No pressure there, right.
Not to mention the pressure on the application programmers who actually had to build the software using these incredibly powerful but complex new tools.
Exciting. Absolutely. Daunting. Oh, yeah.
Speaking of daunting, in the materials you shared, there were 5 major challenges highlighted that programmers face with multi-core. Identifying tasks, balancing the workload across cores, figuring out how to split the data, then there's the whole data dependency nightmare.
Right.
And then, of course, the ever-popular testing and debugging.
Yeah.
I can only imagine the amount of coffee needed to power through that.
It's a lot. Each of those is a rabbit hole of complexity. Maybe we should pick one to focus on for now, just to, keep our sanity intact. What about that data dependency thing? That one seems particularly mind-bending.
It's a great choice and something I think we can all relate to, even outside the world of coding.
Oh, do tell.
Think about it. If one task relies on data from another task that hasn't finished yet, you're going to have a bad time.
Right.
It's like trying to build a house, but the foundation depends on the roof being finished first. Chaos.
Total chaos.
Exactly.
So how on earth do they prevent this digital demolition derby? They can't just hit pause on one core while they wait for another to catch up, right?
You're absolutely right. That's where synchronization tools enter the picture.
Synchronization tools. Okay, you're losing me a bit.
Think of them like traffic lights for data in the multi-core world, making sure everything flows smoothly and preventing any head-on collisions.
So synchronization tools are like the unsung traffic cops of the digital world, making sure all the data gets where it needs to go without any multi-core pileups. I like it. Makes you appreciate all the hidden complexity in our devices, Just browsing the web suddenly seems like a minor miracle.
It really is remarkable when you think about it. Every click, every swipe, it's all powered by this intricate dance of parallel processing.
Speaking of intricate dances, there was this other concept to the research that really caught my eye, Amdahl's law. Sounds ominous, doesn't it?
It does have a certain ring to it.
It's like a reality check in the face of all this multi-core hype. Like, hold on. Even with infinite cores, there's a limit to how fast things can go.
Exactly. Amdahl's law highlights the fact that even with a massive amount of processing power, the overall speed of a program is often limited by the portion that can't be parallelized.
It's like having a team of super fast chefs prepping a meal.
Okay, I like where you're going with this.
No matter how quickly they chop, if the oven only fits one dish at a time, you're stuck waiting.
That's a perfect analogy. Amdahl's law reminds us that it's not just about throwing more cores at a problem, but about understanding the entire workflow and optimizing those critical bottlenecks.
So how do you know which parts are going to be those bottlenecks? What kind of tasks just refuse to be parallelized?
Well, some tasks are inherently sequential by nature. Think about following a recipe. You can't just bake the cake before you've mixed the ingredients.
Right, some things just have to happen in order.
Exactly. In programming, it often comes down to tasks that involve complex dependencies or require data to be processed in a very specific, linear order.
So it's not always a simple case of more cores equals more speed. Sometimes it's about optimizing that one critical path, that single lane highway where everything has to funnel through.
That's a great way to put it. And that's why understanding the nuances of parallel programming is so important. It's about knowing when to leverage the power of multiple cores and when to focus on optimizing those sequential bottlenecks. It's about choosing the right strategy for the job at hand. And that brings us to another important distinction: data parallelism versus task parallelism.
Ah, yes. Two distinct flavors of parallel processing, each with its own strengths and weaknesses.
Exactly. It's like having two different tools in your toolbox. You need to know when to use which one for the task at hand.
Okay, so walk me through it. What are the key differences between these two approaches?
Sure. Imagine you have a mountain of documents to sort through. With data parallelism, you divide the pile evenly among your team, and each person would sort their share independently.
So everyone's doing the same task, but on different chunks of data.
Precisely. It's a classic divide and conquer strategy, like that example in the research about summing an array of numbers. Each core gets its own slice of the array to work on, and then the partial sums are combined at the end.
Got it. Divide the data, conquer the calculations. Makes sense.
Yeah.
But task parallelism is a different beast altogether.
Exactly. Now imagine that instead of just sorting documents, your team is responsible for different stages of a larger project: research, writing, editing, and so on. Each person has a unique role to play.
So instead of dividing the data, you're dividing the tasks themselves.
Right, and these tasks can often be executed concurrently without needing to wait for each other to finish.
Okay, that makes sense. So data parallelism is about efficiently distributing the same task across multiple cores, while task parallelism is more about orchestrating the execution of different tasks in parallel.
You've got it.
It's like we're assembling a dream team, each member bringing their A game to the project.
Exactly.
But, and maybe this is a bit too real world for our tech talk here, sometimes you need a mix of both, right? I mean, not every project can be perfectly divided into neat little boxes.
Absolutely. It's not always an either-or situation. In fact, many real-world applications use a combination of data and task parallelism, a hybrid approach, if you will.
Hybrid approach, I like it. It's like the best of both worlds.
Exactly. Think of something like video editing software. It might use data parallelism to apply filters to multiple frames simultaneously, while also using task parallelism to handle things like audio processing and rendering.
So it's not about picking one strategy and sticking to it. It's about understanding the strengths of each and finding that perfect blend.
Precisely. And that's part of what makes parallel programming so challenging, but also so rewarding. It's like solving a multi-dimensional puzzle, constantly evaluating trade-offs and finding ways to squeeze out every ounce of performance.
It really makes you appreciate what's happening under the hood of our devices. It's like this invisible orchestra playing a symphony of calculations just so we can watch cat videos without a buffering icon.
It's easy to take for granted, isn't it?
It is. But for those of us who like to tinker, it's fascinating to peek behind the curtain. So speaking of tinkering, what kind of tools are we talking about here? How do programmers actually wrangle all this multi-core magic? Is it some kind of secret coding language?
Well, it's not exactly a secret language, but there is a whole ecosystem of tools and techniques designed specifically for parallel programming.
Okay, so walk me through it.
Depending on the project and the programming language, developers might use things like threading libraries to manage concurrent tasks, or message passing interfaces to coordinate communication between cores. It's a constantly evolving field with new tools and techniques emerging all the time.
So it takes a special kind of programmer to master this stuff.
It definitely requires a shift in mindset. Instead of thinking sequentially, you have to start thinking in parallel.
Sounds like a workout for the brain.
It is. But the ability to harness the power of multi-core processors is becoming increasingly valuable.
Especially with things like AI and data science taking center stage. I mean, without multi-core processing, those fields would grind to a halt, right?
Absolutely. Multi-core processing is the engine driving those innovations, allowing us to process massive amounts of data faster than ever before.
It's amazing to think that something as seemingly abstract as parallel programming can have such a huge impact on so many aspects of our world, from the apps on our phones to cutting-edge scientific research.
It's everywhere.
And who knows what the future holds? I mean, we've gone from single-core to multi-core, but what's next? Are we going to see CPUs with hundreds, thousands of cores?
It's certainly possible. The technology is constantly evolving.
It's mind-blowing. Well, we've covered a lot of ground in this deep dive. We talked about the challenges of concurrency, the limits of parallelism, the different flavors of parallel processing, and even the tools programmers use to wrangle this multi-core beast.
It's been quite a journey.
It has. But I think the biggest takeaway for me is that multi-core processing isn't just some abstract concept confined to the world of computer science. It's the engine that powers our digital lives, whether we realize it or not.
And understanding how it works, even at a high level, gives you a new appreciation for the invisible forces shaping our world.
Absolutely. So as we venture further into this age of multi-core, it begs the question, what new possibilities and challenges await? What breakthroughs will it enable? What new problems will it create? These are the questions worth pondering. Until next time, keep exploring, keep asking questions, and never stop marveling at the wonders of technology.
All right, get ready to dive deep, because today we're all about multi-threading models.
Really fascinating stuff, how our computers juggle so many tasks at once.
Right. It's like they're doing a million things simultaneously, pure magic. But for those of us who don't speak fluent computer, what are threads? Why should we care about them?
Well, imagine your computer has this to-do list.
Okay,
Each item on that list is a thread, a task, a process.
I'm with you.
Now, multi-threading, it doesn't mean your computer is literally doing all those things at the same exact time.
Oh, okay.
It's more like rapidly switching between them.
So less simultaneous, more like super speed juggling.
Exactly. And just like a juggler needs to keep all those balls in the air, the operating system, it needs a way to manage all those threads.
Right, makes sense.
That's where these multi-threading models come in. They're like the strategy for managing all that action. But to really get into the models, we got to talk about user threads versus kernel threads.
Okay, hit me with it.
Picture this. You walk into a bustling restaurant kitchen.
Ooh, I'm already hungry, but go on.
You've got a diagram of this kitchen. We'll be sure to link one in the show notes, but picture it bustling. Cooks everywhere, right? Those cooks, they're like the user threads.
Each one working on a different dish or task.
You got it. Now imagine a little window connecting the kitchen to the dining room.
Okay.
That window, that's the kernel thread, the direct line between those busy cooks, the user threads, and the outside world, the operating system.
So the cooks or user threads might be doing their thing, but they need that window, the kernel thread, to communicate with the diners, the OS.
Precisely. And how that communication happens, well, that depends on the multi-threading model in play.
Makes sense. So what's first up?
First up, we've got the many-to-one model.
Many to one, sticking with the kitchen. That sounds like a recipe for disaster. Like a whole bunch of cooks trying to squeeze through one tiny window.
Haha, you're catching on quickly. That's the thing with many-to-one, it's simple. Multiple user threads all trying to use that single kernel thread to talk to the operating system.
Okay, but I could already see the problem. Like if one cook needs something or there's a holdup, wouldn't everything just stop?
That's the limitation, yeah. While it was an early attempt and its simplicity is appealing, it lacks true parallelism.
So many to one, maybe not so efficient for our modern computer lives.
Not quite. Especially with multi-core processors now, it's like having multiple kitchens, right? And that brings us to the one-to-one model.
One to one, that sounds a bit more, I don't know, efficient? Tell me more.
All right, picture this. One-to-one, we ditch the single window. Every cook gets their own dedicated window to the dining room.
So each cook, each user thread has a direct line to the operating system. No more waiting around.
Exactly. This direct mapping means each user thread gets its own kernel thread, no more bottlenecks.
That's going to be a game changer, especially with multi-core processors now, right? So one-to-one, that's it, right? Problem solved, multi-threading bliss.
Well, you'd think so, wouldn't you? It seems like the perfect solution, and honestly, it was a huge step forward, but...
Uh-oh, there's a but, isn't there?
Yeah.
Always a catch.
Like with so many things, you know, life, computing, there are trade-offs.
All right, I'm listening. What's the downside to all this one-to-one efficiency?
Okay, so back to our kitchen.
Still hungry.
Right. Instead of just a few cooks, imagine, say, 100 cooks,
Go away.
each with their own window to the dining room.
That's a lot of windows, even for the fanciest kitchen.
Exactly. So while one-to-one is great for concurrency, letting all those tasks run independently, it can be a lot for the operating system to handle, especially with loads of threads.
So too many cooks, or in this case, too many windows.
You got it. It gets complicated, adds overhead, managing all those kernel threads.
So what, we need like a multi-threading Goldilocks situation? Not too much, not too little.
Exactly. And that, my friend, is where the many-to-many model comes in, trying to strike that perfect balance.
Many to many. Okay, now you're just messing with me.
Yeah.
How does that even work?
All right, new analogy time. Let's shift gears. Imagine a team of super skilled workers.
Yeah.
These are our kernel threads. Instead of a head chef, think project manager. That's our operating system.
I'm with you. Skilled workforce, savvy manager.
Right. In the many-to-many model, the project manager assigns tasks, our user threads, to the best worker for the job based on their skills, workload, that kind of thing. It's adaptable, optimized.
Okay, so it's dynamic. Resources are allocated on the fly for maximum efficiency.
Exactly. That's the beauty of it. High concurrency, but without going overboard on resources. And for those who like a bit more control, there's the two-level model, which uses bound threads.
Bound threads, that sounds intense. Like we're tying a thread to a specific job, is that right?
That's a good way to put it. With bound threads, you can pre-assign certain user threads to specific kernel threads. It's like, okay, this worker, they're always on standby for this particular project.
It's a little pre-planning in our dynamic system. I like it.
Right, it adds a layer of control. Now, I know what you're thinking with all this flexibility, this efficiency. Is the many-to-many model the ultimate winner?
It's certainly sounding like a top contender. It's like this model has seen it all, learned from everyone else's mistakes.
It was definitely seen as a front runner for a while, and for good reason. But as with technology, what's revolutionary one day?
Becomes old news the next. So what happened? Is there a new multi-threading sheriff in town?
Well, let's just say the rise of multi-core processors changed the game completely.
Ah, those multiple kitchens we talked about. So what was the problem? Became the solution.
Exactly. More cores means that potential overhead from managing lots of kernel threads, not such a big deal anymore. The one-to-one model, with its direct mapping, true parallelism, it just made more sense.
It's wild to think what's next. Quantum computing? AI managing threads? Who knows? But for now, I think we're all multi-threading experts, right?
Well, maybe not experts, but we've definitely learned a lot today.
We have. So as we wrap up our deep dive into the world of multi-threading models, what's a big takeaway for our listeners?
I'd say next time your computer's going crazy, doing a million things at once, take a second to appreciate the behind-the-scenes magic. These models, from the simple many-to-one to the elegant one-to-one, they make our digital lives possible.
I love that. This hidden complexity we never even think about.
It's true. And as technology keeps advancing, who knows what new models, what new innovations are coming. Exciting time to be into computers, that's for sure.
It really is. Well, a huge thank you to you. This has been such a fascinating conversation.
Thanks for having me. Always a pleasure to geek out about operating systems.
And to all our listeners, thanks for joining us on this deep dive into multi-threading. Catch you next time for another exciting look at the tech that makes our world tick. All right, ready to dive in. Today we're tackling multi-threading. And let me tell you, it's a wild ride. Imagine like a chef trying to juggle cooking like 5 different dishes at once. Each needs different ingredients, different cooking times, and they're constantly switching between tasks.
Exactly. It's all about maximizing that efficiency, right? Think if your web browser completely froze every time and had to load a new image, or if you had to wait for one app to totally close before opening another. Multi-threading is how our devices juggle all those tasks at once.
And in this deep dive, we're going to try to understand the challenges that come with that juggling act. We've got some excerpts from an operating systems textbook, really breaks down the big issues the developers face when they're trying to design multi-threaded programs.
Even if you're not a coder, though, getting these challenges, I think it gives you a whole new appreciation, for how software is actually built.
Okay, so let's jump right into challenge number 1. Creating new processes. So imagine like a giant family tree,
Yeah.
and at a certain point you want to like branch off a whole new section.
Right.
In the programming world, that's where the fork system call comes in.
It's like you're making a carbon copy of that family line at a specific moment. But here's where it gets really interesting, is that with fork, developers have to choose. Do they want this new process to inherit everything from the original, like every single family trait that's been passed down? Or are we talking just the basic framework and starting fresh?
So if the original process is like this bustling household, with all these different people doing different things, by the way, those are threads. So with Fork, you can choose. Does the new process get its own copy of every single person doing those things, or does it start with just like one person in an empty house?
And that choice has huge implications.
Yeah.
Huge. Let's say you've got like a web server that's handling tons of requests. If it uses Fork to make a new process for each request, it needs to decide, are these new processes inheriting all the existing connections, or are they starting from scratch? Getting that wrong, I mean, that could cause performance issues or even crashes.
Yeah, it's that balance between efficiency and not overloading the system, right?
Absolutely. Now, sometimes instead of branching off, you want to just completely replace one process with something totally different. This is less branching a family tree and more like one branch just packs up, moves to a new country, adopts a whole new way of life. That's where the exec system call comes in.
So instead of a copy, you're basically swapping out that entire process with a whole new program.
Exactly. And the source material really emphasizes this, that understanding the difference between those approaches, fork versus exec, it's crucial. It's like picking the right tool for the job, right? And especially when you bring threads into the picture, it gets even more complex.
Well, speaking of complex, let's move on to challenge number 2. Signal handling. Okay, imagine you're at a party, music is blasting, people are talking, and suddenly someone's trying to get your attention. That's basically what a signal is in the operating system world, right? Like a way for these processes to get notified about important events.
Right. But just like at a loud party, not all those signals are created equal. Some need your attention right away, like an urgent phone call. That's what we call a synchronous signal.
And then there are those random buzzes in your pocket, You don't know who it is, you don't know when it came in, you might not even check it till later. That's kind of like an asynchronous signal just pops up whenever.
Yeah, and that unpredictable timing
Yeah.
makes asynchronous signals a real pain when you're dealing with multi-threading. Like, let's say one thread gets a signal to shut down. If it doesn't handle it gracefully, it'd be like ripping the power cord out of the wall. Could leave the other threads in a corrupted state, lose data, even crash the whole system.
So it's like that party you mentioned, someone yells fire,
Mm-hmm.
and everyone just runs for the exits without any thought, could cause a lot more problems.
Yeah, totally. Like a stampede at a rock concert, right? Everyone rushing for the exits, someone's going to get hurt. So handling signals smoothly in a multi-threaded environment, especially those unpredictable asynchronous ones, that's super important. It's like the difference between like carefully landing a plane versus just nosediving it into the ground. Which brings us to, kind of related, our next challenge, thread cancellation. Let's say you got this team working on a big project. One person suddenly realizes, oh, I've had a dead end. This isn't working. They wouldn't just abandon everything without a word, right? Leave everyone else scrambling.
No way. That's a recipe for disaster in a team, for sure.
And that's kind of the problem with what we call asynchronous thread cancellation. It's like hitting that kill switch without giving the thread any chance to clean up, release resources, let the other threads know what's up.
So instead of a clean handoff, it's more like they vanished into thin air, leaving all their work scattered everywhere.
And that is why we have deferred cancellation. This is all about giving the thread a chance to wrap up gracefully. It can release the resources it's holding, notify other threads, basically avoid a chaotic mess.
So more like instead of disappearing, they say, hey, I hit a dead end, I'm going to document what I did, save my progress, then I'm out.
Exactly. And this idea ties into what developers call cancellation points. It's like setting up designated stopping points on a long journey. You wouldn't just stop a train in the middle of nowhere, you'd pull into a station.
Right. Makes sense. And what about these cleanup handlers the source mentions? Are those like the notes left behind by our departing team member?
Exactly. Cleanup handlers, those are blocks of code that get executed when a thread's being canceled. They're there to release resources the thread might be holding, like closing files or releasing locks so nothing gets messed up.
So it's all about leaving everything in a good state, even if a thread has to make an unexpected exit.
Right. Now, shifting gears a bit, let's talk about this other challenge. Making sure each thread has the data it needs without stepping on each other's toes. Imagine like a classroom full of kids, each working on their own project. They wouldn't all share one giant pencil case with like one eraser and two crayons.
Oh, the chaos. That would be a recipe for disaster.
Exactly. And that is why we have thread local storage, or TLS. It's like giving each kid their own personal pencil case. No more fighting over shared resources.
So instead of having every thread potentially trying to access and modify the same global variables, which I can only imagine leads to a mess of conflicts, each thread gets its own little private storage locker.
Yeah. You got it. It's like having separate lanes on a highway, right? Each thread can just zoom along in its own lane, no risk of colliding with others. And this is super important. The source material really emphasizes this for threads that have to manage unique identifiers or roles.
So like if one thread's handling user authentication and another's processing payments, TLS makes sure their data doesn't get mixed up. Like keeping those student projects nice and separate, no accidental plagiarism going on.
Exactly. And the cool thing is, even though how you do it, the syntax might be different across programming languages. You know, the source mentions Java, Threads, C#. The basic concept stays the same. Give each thread its own space. Fewer conflicts, better security.
Keeping order within the chaos, I like it.
Right. All right, you ready to tackle our final challenge? This one's all about what's going on behind the scenes. Remember that juggling chef from earlier? Well, now imagine instead of one chef, we got a whole team of them, each with their own specialty dishes.
Okay, a whole team of chefs, each with their own station, their own specialty. I mean, it sounds amazing for the diners, but yeah, I could see how that could easily turn into chaos in the kitchen without someone keeping things running smoothly.
Right, and that's where this idea of scheduler activations comes in. Think of it like you got a head chef overseeing the entire operation, right? Making sure each chef gets the resources they need when they need them.
Instead of everyone just grabbing ingredients in pans all willy-nilly, which, yeah, could lead to some bottlenecks for sure.
Exactly. So in operating systems, that head chef is the kernel, and each individual chef, that's like a lightweight process, or LWP.
LWP is right. They're kind of like the go-between, right, between the threads, actually doing the cooking, chopping veggies, all that, and the kernel, which is managing all the resources.
Oh, got it. Like sous chefs, making sure the orders and ingredients are flowing between the head chef and the line cooks. Now, the LWPs communicate with the kernel through things called upcall.
So an upcall, that's like the sous chef running up to the head chef like, "Chef, we're almost out of olive oil over here."
Exactly. It's a way for the LWP to signal that it needs something. But here's where scheduler activations get really clever. See, instead of just reacting to each individual upcall, the kernel can actually anticipate what the LWPs are going to need. It can proactively allocate resources based on the workload, how important each task is, all that.
So it's like the head chef can see which stations are about to get slammed and make sure they're prepped and ready to go.
Exactly. Maximizing efficiency, minimizing delays. And the source material really highlights how important this is, especially on systems with multiple processors or multi-core processors. It's like having more stoves and ovens in our kitchen analogy, right? Scheduler activations make sure everything's humming along, using all that available power.
So instead of everyone crowded around one tiny stovetop, they've each got their own space, can work in parallel. That makes sense.
Right. Like a well-conducted orchestra, each instrument playing its part. So we've covered a lot of ground here. Forking processes, those signals, threads, data isolation, now even scheduler activations. It's pretty mind-blowing when you think about it. All this happening under the hood every time we use our phones, our laptops, whatever.
It really is. And even though we've only scratched the surface, it's like you start to appreciate the complexity of it all. Like we said earlier, even if you don't write a line of code, you understand how much work, how much thought goes into making our devices work.
Absolutely. And it makes you wonder, right, as technology keeps advancing, what new challenges will pop up? What new analogies will we come up with to explain them even?
That's a great question to leave our listeners with. But one thing's for sure, multi-threading, it's not going anywhere. It's only going to get more complex, more powerful. So next time your device is juggling a million things without breaking a sweat, take a second to think about those threads working away behind the scenes.
A whole hidden world making our digital lives possible.
And on that note, that wraps up our deep dive into multi-threading. Hope you enjoyed it. Until next time, keep those threads running smoothly.